What does a capacitor try to keep constant? Voltage or current? Jacob.
Current. It tries to keep the current constant.
The inductor does, yeah. It tries to keep current constant. That's right.
I'm sorry, were you talking about a capacitor or
I was.
inductor?
Yeah, I actually asked about the capacitor. And the capacitor was the example we gave over here, where he said that capacitor will try to keep that what constant, Jacob?
Voltage.
Voltage, yeah. Because of this relationship up here, if it sees the voltage changing, it'll develop a large current to try to keep it from changing. So it tries to keep the voltage. Capacitor, it keeps the voltage constant, tries to. In as much as energy it has stored in its diaphragm, and the inductor will try to keep the current constant as much as it can, given the amount of energy stored in the inertia in the long pipe. And just like Kyle said, the way that a capacitor really stores the energy is not in an elastic diaphragm, but in an electric field. The inductor will store energy in a magnetic field.
Sir?
Yeah.
I'm just curious. If you combine the two together, put a conductor near an inductor.
We'll talk about that.
A capacitor near an inductor. Can you just kind of create electricity, put like a wire between the magnetic electric fields, or like some kind of metal conductor through it?
Well, you don't need to actually put them physically close together. You can just connect them with wires. And what they'll do is they'll trade energy back and forth between a magnetic field and an electric field, and they'll just oscillate back there forever. And we will talk about that soon, but not right now.
Okay, because I just heard that's how a lot of wireless chargers have developed.
Right now we're gonna look at them independently, and then I promise, Kyle, we will add them together. The math equations are I equals C dV dt, and you can solve that for voltage, which is 1 over C times that integral from T naught to T of the current plus that initial voltage. And then one other thing is the energy. We said is 1/2 CV squared. We've already covered that. And then to find power, it's always I times V. So look at what's going on with an inductor. Over here, I'll just give it to you. V is equal to L I prime. Notice how similar it is to capacitors. We're just changing C's for L's and I for V's. They're sort of like inductors and capacitors are inverses of each other. So therefore, your I is going to be 1 over L times that integral over V of tau d tau plus your initial condition. And without even telling you what it is, Jack, can you tell me what the energy is in an inductor just by looking at the capacitor formulation? And I'll start you off. 1/2. Linda, how about if you help him out?
1/2 L I squared.
That's it. And that is how much energy is stored inside that magnetic field. Okay, DC response. We said capacitors, after a long time, they get charged up and they end up just looking like an open. A inductor becomes a short. Our intuition is right back here. After a long time, it's like the inductor isn't even there. Oh, and I'm going to go back to this. V equals Li prime. Look at this. Here's our V. Here's our I. If we take the derivative of this, we get here. The slope here is positive, and the highest it ever is at the very beginning. The voltage here is the highest it's ever at the beginning. The slope here slows down and eventually goes to zero slope. The voltage slows down and eventually becomes zero slope. What's the slope of a negative going line? It's infinitely negative. Here's our infinitely negative spike. And then somehow it has to get back down to zero here where it's flat, and it's zero flat. So we can kind of deduce, again, the math just from our intuition. How about the construction? we said that there is a formula for the construction. It's the area of the plates divided by the distance between the plates, and there's some linear factor out here, which we call epsilon. For an inductor, there's another different linear factor, and it's equal to the number of turns of your inductor. You actually make an inductor by just coiling a wire around times the area enclosed by those turns over the length of the inductor. You don't need to know that for the test. I just want you to have seen it someplace. How do they work in series and parallel? So for a capacitor, it's the opposite of a resistor. And for an inductor, you can probably already see it. Watch this. We've got one inductor, and we're going to put it in parallel with another inductor. Think about the hydrodynamic analogy. We've got one set of coiled pipes, and we're going to put it in series with another set of coiled pipes. Do you think the total inductance will increase or decrease? Connor?
Increase. So
It'll increase. And so it's going to be the same as a resistor. Inductors in series add, and inductors in parallel have that weird 1/over relationship. And let's just talk about that, because I had a question last night about this. What is this 1/over relationship thing? If you have 3 or more inductors, the equivalent inductance has to be figured out by this equation. I mean, you could add more and more of them over here if you wanted to. ... Check out what the units are. 1/Henries plus 1/Henries plus 1/Henries. You're going to add them all up. The denominator will be 1/Henries. 1 over that will give you Henries. So the units make sense. In the particular case that you only have 2, whether inductors or resistors, while it is true that it's equal to this, it's a whole lot easier figuring it out by product over sums. Algebraically, these two things are related. So this is in series, this is in parallel. Algebraically, these two things are the same. It's just a lot easier to compute this practically, and you can do that in your head than this, which requires a calculator. But if you got 3 or more capacitors in series or resistors or inductors in parallel, you have to use this long one. There's no choice. Okay, and then in op amps, we said we do KCL at the inputs. And we don't use inductors with op amps. Here's the real world thing that the text doesn't say. Capacitors are crazy good. They're really small physically. As Kyle pointed out last class, their electric field is really limited, tightly limited right to where those capacitors are. It doesn't leak beyond the capacitor, so they don't interfere with each other. And real world capacitors are amazingly close to these ideal capacitors we've been studying. Yeah, it's true that an actual real world capacitor does have some series equivalent resistance, and it does have some non-infinite parallel resistance. But this thing is usually measured in mega ohms, and this thing is usually measured in milliohms. And so it's really, really close to an ideal capacitor. Not true for an inductor. An inductor has a big equivalent series resistance. Why? Because it's just a big long coil of wire. So of course it's going to have a big resistance. And because an actual inductor does not look that close to a ideal inductor, we don't like to use them as much. Secondly, a real inductor creates a magnetic field around it. And this magnetic field extends out of it quite a bit. Looks like that, if you could visualize it in 3D, like a donut going right around it. If you have 2 inductors that are close to each other, those magnetic fields interfere with each other. and they end up becoming a transformer, and then they don't behave ideally at all. So in general, we try not to use inductors if we can. Capacitors are smaller and they are cheaper and they work better. In fact, if you need an inductor, you probably want to use a capacitor inside an op-amp in a way that can make it look like an inductor. And that will be an exercise for a future class. Any questions about all this stuff? We covered a lot of material.